Okay, welcome back everyone. In this video, we're talking about trigonometric identities. We'll be proving trigonometric identities hold, and before we get there, we need to talk about what an identity is. And that's just any equation which is always a true statement. So something like this, x minus 1 equal to 2x minus 2 over 2, that's an identity because no matter what value you put in for x, the left side and the right side will always be equal to each other. And we can see that if we examine the left side and the right side separately. The left side is just x minus 1, and the right side, that's 2x minus 2 over 2. If you were to simplify that, dividing top and bottom by 2, you would be left with x minus 1 over 1, and of course that's the same thing as just x minus 1, which is the left side. So in other words, the right side is always equal to the left side no matter what value for x we put in. Now, on the other hand, something like this equation, x minus 1 equals 5, that's not an identity. It's sometimes true, so if x were 6, that would be a true statement. You would have left side equal to right side, but for any other value of x, it's not a true statement. This would be something that you would call a conditional equation. A conditional equation is one that's not always true, or is only true for some values of the variable. But what we're looking at is equations that are always true statements. And we've seen a bunch of these already. We have our even odd identities that we saw before. That's something that's always true, no matter what the angle is. The reciprocal identities that we have relating secant and cosecant and sine, tangent and cotangent. We also have the Pythagorean identities. We also have some other ones that I didn't write down, because they don't really have fancy names. But it's that, for example, tangent of theta could be rewritten as sine of theta over cosine of theta. The idea that you could take any trig function and rewrite it in terms of sines and cosines. Same thing with cotangent. You could turn cotangent of theta into cosine of theta over sine of theta. That would also be a always true statement or another identity. Now, for these Pythagorean identities, they will come up a lot, so it's good for us to see them again, and we're going to prove them again, because recognizing when those identities can apply, realizing that, oh, we see a cosine squared in an equation, oh, I can rewrite that in terms of sine squareds. That's a skill that's going to come back again and again and again as we make our way through this section. So now, deriving my three Pythagorean identities, when we did this before, back in chapter 7, I did this using right-angle trig as my argument. I used the Pythagorean theorem to help me out there. But here we're going to be talking about angles inside a unit circle. And remember, for angles inside a unit circle, you take a point, x, y, that's on the unit circle for that angle theta. And the thing that makes things easier here, of course, is if you're in a unit circle, the equation for that is x squared plus y squared is equal to 1. So that means you actually can start out right away just saying, well, we know that x squared plus y squared is equal to 1 because the point that we're talking about, xy, that's a point on my unit circle. And then now I'm just going to use the definitions that we had for trig functions in the unit circle. X was cosine, so x squared would be cosine squared theta. Y was the sine function, so y squared would be sine squared theta. And there we go, we have our first identity. For the second identity, remember when we did this before, we derived the second and third trig identities from taking that first identity. So taking cosine squared theta plus sine squared theta equal to 1, and then dividing everybody by either sine squared theta or cosine squared theta. If you divide everybody by sine squared theta, well, cosine over sine, that is cotangent, so cosine squared over sine squared, that would be cotangent squared theta. Sine squared over sine squared, that's just 1. 1 over sine is cosecant, so 1 over sine squared, reciprocal of sine squared would be cosecant squared. And there we go, we have our second identity. And the third identity I'll do in exactly the same way. I'll take my first equation that I have here, and instead of dividing everybody by sine, I'll instead divide everybody by cosine squared. So let's do that. So from equation 1, we had cosine squared theta plus sine squared theta is equal to 1. And if I divide everybody by sine squared theta, oh, I already did that one. If I divide everybody by cosine squared theta, cosine squared over cosine squared is 1. Sine over cos is tangent, so sine squared over cosine squared is tangent squared. 1 over cosine is secant, so 1 over cos squared is secant squared theta, and there we go, that is the third identity. Now, one thing that we have to get used to, and this is just foreshadowing for the future, is seeing these identities in different forms. So the way that I wrote it down here, 1 plus tangent squared is equal to secant squared, that's true, but of course, that could also be rewritten in a bunch of other ways. You could say, for example, tangent squared theta is equal to secant squared theta minus 1. Or you could say secant squared theta minus tangent squared theta is equal to 1. So depending on what we have, if we have secant squared by itself, or a tangent squared by itself, or a secant squared minus a tangent squared, I might use any one of these three forms. And of course, they're all interchangeable. They just happen by taking one thing and moving it to the other side of the equation, whether it's the tangent or whether it's the secant. That they're all equivalent to that third identity. And the same thing, of course, is true for all the other Pythagorean identities. All right, so before we establish identities, we need to talk about simplifying trig expressions, which we haven't really done a whole lot of yet. Here, this is something where we're going to need to manipulate some trig expressions, and there's a bunch of different techniques that are possibly helpful depending on the scenario. So one thing that could be useful would be rewriting things in terms of sines and cosines, and that's especially true if you see a lot of tangents and cotangents and secants and cosecants. So that's my idea here. I've got sine times secant times cotangent, and secant I can rewrite as 1 over cosine, and cotangent, that is cosine theta over sine theta. There we go. And at that point, things are pretty much finished because I can see that the cosine and the cosine will cancel, and the sine will cancel. So really, I'll just be left with 1. So actually, the expression that we started with, sine times secant times cotangent, it simplifies to just be equal to 1. Another one, which is using even and odd identities, and this one's kind of obvious. If you see a trig function where there's a negative angle, that's your hint. Think about using those even and odd properties of your trig functions. So I would use the fact that cosine is an even function, so cosine of negative theta is the same thing as cos of theta. Sine is an odd function, so sine of negative theta is negative sine of theta. And then from that point, I also notice I've got negative over a negative, so that'll become positive. So I'll be left with positive cosine theta over sine of theta. Oh, wait, hold on, that's our old friend cotangent. So there we go. Cotangent theta is what our expression simplifies to. So negative cos of negative theta over sine of negative theta, same thing as cotangent. Pythagorean identities. If you see a sine squared or a tangent squared or any trig function squared, that's your tip-off to think about a Pythagorean identity, especially if you see things like tangents and secants in the same equation. Your Pythagorean identity relates those two, or sines and cosines, or cotangents and cosecants. I'm looking at this at tangent cubed over secant squared x plus 1, and I'm just going to remind myself that the trig identity that we had, which was tangent squared plus 1 equals to secant squared, that you could rewrite that identity by moving the plus 1 to the other side of the equation, so that you would actually say that tangent squared x is equal to secant squared x minus 1. So that's going to be my idea here, that the denominator that I have, I'm going to actually just replace that with tangent squared minus 1 using my Pythagorean identity. So the numerator is tangent cubed x, and the denominator is equivalent to tangent squared x. And then we have 3 tangents up top, tangent times tangent times tangent, and we've got 2 in the bottom. So the 2 tangents in the bottom cancel with 2 of the 3 tangents that are up top, and that leaves me with 1 tangent of x that's left over in the numerator. So my expression simplifies down to give me just tangent of x. All right, let's do a couple more. Factoring. Again, a lot of these are possibilities, and in fact, there's lots of possibilities that you could do even just with this one expression. So, for example, something like tangent, you might turn that into secant squared minus 1. That might be one option of something you could do. Or tangent squared could be turned into sine squared over cosine squared. That might be another option that's also feasible. But one other thing that is a possibility is, just like we had before for algebra, polynomials, if you see a common factor, why not factor it out and see if that makes your life any better? We have 2 terms here, and I see that cosine of theta is a factor for both, so that's my idea. I would factor out cosine of theta, and that would leave me with tangent squared theta plus 1. And at that point, hopefully bells are going off in your head. You're thinking tangent squared plus 1. That is the same thing, of course, as secant squared. That's that Pythagorean identity from before. Secant squared theta is tangent squared plus 1. And then I'm thinking secant and cosine, oh wait, those are reciprocals of each other, so why don't I turn secant into 1 over cosine? So secant squared is 1 over cosine squared. Oh wait, things are going to cancel now. I have a cosine in the numerator that can cancel with one of the cosines that's in the denominator. I'm left with 1 over cosine of theta. And 1 over cosine is the same thing as secant of theta. So this expression simplifies down to giving me just secant of theta. Okay, one last thing that you can do would be to create a difference of squares. And the reason for this, and we're just going to circle back to our Pythagorean identities for just a minute, all of these Pythagorean identities could be rewritten as a difference of squares. So for example, this could be rewritten as sine squared theta being the difference of squares 1 minus cosine squared theta. So if you were able to make a 1 minus cosine squared happen, then you could replace it with sine squared. Or, I mean, equivalently, you could take it and say that cosine squared theta is 1 minus sine squared theta. So if you were able to make a 1 minus sine squared happen, you can turn that into cosine squared. And the same thing could be said for the other 2 equations. They could be rewritten as the second one, cosecant squared minus cotangent squared equal to 1, or 1 minus cosecant squared is negative cotangent. There's lots of different differences of squares that exist that could be found from these Pythagorean identities. So that's the idea here, is that if we have something that's not a difference of squares yet, and it's a 2-term expression, we can make it into a difference of squares. So the plan here is, I see this tangent of x plus secant of x in the denominator, and I know that if I were to multiply top and bottom by the conjugate, tangent of x minus secant of x, top and bottom, I know 2 things. Number 1, that on the top I would have cosine of x times all of that, tangent x minus secant of x. And in the bottom, when we multiply these 2 together, tangent plus secant times tangent minus secant, remember a plus b times a minus b is a square minus b square. So when I multiply those together, I'll get tangent squared x minus secant squared x. And that's kind of a lovely thing, because if we're thinking about that Pythagorean identity that tangent squared plus 1 is equal to secant squared x, if you were to move the secant squared to the other side and then move the 1 to the other side, you would have on the left side tangent squared minus secant squared, which is exactly what we have, and on the right side you'd have negative 1. So in other words, tangent squared minus secant squared is the same thing as negative 1. So this is what I'll do now. I'll just say that, great, the denominator is negative 1, so in other words we have negative cosine of x. And I'm actually going to do a second step here, because I see I've got tangents and secants, and I know that if I were to turn those into sines and cosines, that actually would be something that would be useful for the next step when I multiply everybody together. So sine over cosine, that's tangent, and 1 over cosine, that is secant. And then lastly, what we need to do is just multiply things together. When I multiply the negative cos x times the tangent times sine over cosine, when I multiply those together, the cosines cancel, and I'll be just left with negative sine x. When I multiply together the negative cos x and the negative 1 over cos x, the cosines cancel, the negatives cancel, I'll just be left with plus 1. So when I expand and cancel things out, I'm left with negative sine x plus 1, or maybe it looks a little bit nicer to write that as 1 minus sine of x. All right. So there we go. Those are some of the options that we will be working through when we're establishing our identities, and we might use one or more of them in any given problem. So this is something where we need to be looking at what we're working with and thinking about what does it suggest for us to do. So if you see squares, you might be thinking about using a Pythagorean identity. If you see a bunch of terms with common factors, maybe factoring. You see negative angles, think about using your even and odd identities. That's the way that I want us to be thinking as we're working through the identities that we're going to be establishing. But for now, we'll take ourselves a brief break, make ourselves a fresh cup of tea, and then when we come back, we'll talk about how to establish a trig identity.